In today's lecture, I am going to derive the phase rule equation and then tell you how to use this equation in dealing with a phase diagram. Let me start with the definition of phase rule. Again, if a system at equilibrium is unaffected by electrical, magnetic and gravitational forces, and if it depends only on temperature, pressure and composition or concentration, then the number of phases P, the number of components C and the number of degrees of freedom F are related by the phase rule equation. The equation is F is equal to C minus P plus 2. Now, let us consider a system, a big one at that. It is a heterogeneous system consisting of P number of phases and C number of components, and we name the phases as A, B, C up to P, and we name the components as 1, 2, 3, 4 right up to C. For convenience, we assume that all the components are present in all the phases and the concentration of a given component, say 1, may be different in different phases. The system is a closed one and it is in thermal and mechanical equilibrium. That is to say that the pressure and temperature are the same throughout the system. We make an assumption here. There are no chemical reactions between the substances in the system. Otherwise, there will be restriction imposed on the system. We also assume that the system is unaffected by electrical, magnetic and gravitational forces. To calculate the number of degrees of freedom of the system, first we have to add up the total number of intensive variables required to describe separately each phase, and then subtract the number of those variables whose values are fixed by the equilibrium relations among different phases. We know that the state of the system depends on temperature and pressure. So, these are the two variables which we always consider, and then look for the concentration variables. There are C components. We have to find out, is it necessary to specify the concentration of all the C, but we know that if we express the concentration in mole fractions, it is sufficient to mention the concentration of C minus 1 components. The last one becomes automatically fixed because sum of the mole fractions of all the components must be unity. Since there are P phases, there will be a total of P into C minus 1 such composition variables. Along with pressure and temperature, now the total number of intensive variables will be P into C minus 1 plus 2 if the system is considered phase by phase. Now, let us find out how many of these variables are fixed by the equilibrium conditions. Now, this by definition, number of degrees of freedom is the number of independent variables. Let us see, for that an equilibrium between two phases A and B containing components 1, 2 and 3 in equilibrium, and the chemical potential mu of these three components in the two phases can be represented as mu 1A, mu 2A, mu 3A, and in phase B mu 1B, mu 2B and mu 3B. As the system chosen is a closed system in equilibrium at a definite temperature and pressure, we can apply Gibbs-Duhem equation to this, which says summation of mu I dni is equal to 0. Let us now transfer a small amount of component 1, that is dn1, under equilibrium conditions from phase A to phase B, and apply gives Duhem equation to this, which gives us minus mu 1 a dn1 plus mu n 1 b dn1 is equal to 0, which tells us mu 1 a dn1 is equal to mu n b dn1. In other words, what we get is mu 1 a is equal to mu 1 b. At equilibrium between two phases, the chemical potential of a particular component is same in each of the two phases. We can extend it and make a general statement. Thermodynamics tells us that equilibrium between various phases in a system is possible only provided the chemical potential of each constituent of a phase is equal to the chemical potential of the same constituent in every other phase. But different constituents can have different chemical potentials. But we also know that the chemical potential of a component in any of the p phases, if it is defined, therefore, its chemical potential in the other p1 phases cannot be varied, and chemical potential are related to concentrations, and therefore, if concentration of a component in any one of the phases is arbitrarily fixed, its concentration in the remaining p1 phases would be automatically fixed, because it becomes non-variant, which means for this particular component p1 composition variables are fixed, and if we consider all the C components present in the system, the number of composition variables thus fixed would be C into p minus 1. And if we subtract this number C into p minus 1 from the total number of possible variables for the system, we will be getting the number of variables of the system which can be arbitrarily chosen, that is p into C minus 1 plus 2, that is the total number of intensive variables, minus C into p minus 1, the number of variables that are fixed by the system, or we can rewrite it as C minus p plus 2. The number of degrees of freedom is nothing but the net arbitrarily adjustable intensive variables. Therefore, we can write F is equal to C minus p plus 2. This is nothing but Gibbs phase rule equation. A simple equation to look at, and the derivation that we considered is also appear to be very simple, but we have given a simplified derivation of this rule. Now, let us see what are the conditions under which this rule is applicable. We had assumed that each component is present in every phase. If a component is present to a negligible extent or not present at all in any one of the phases of the system, there will be one fewer intensive variable for that phase. Since the negligible concentration of one species is of no interest to us, there will also be one fewer equilibrium relation to subtract. So, it makes no difference whether all the components are present in all the phases. And also another point to remember here is that the phase rule is applicable to only the systems which we generally call ordinary chemical systems. If any of the systems are subject to electrical, magnetic or intensity of light, then such additional intensive variables may have to be considered, and the equation may be written as F is equal to C minus P plus 3 or 4, depending on how many of these variables which are otherwise not considered are included. Now, we can see how to use this equation. The systems can be very complicated. There can be a system in which there is one solid, one liquid and a gas phase, but there can be systems in which multiple solid phases, multiple liquid phases can be there. Therefore, such systems can be really complicated. To get an idea how phase rule equation can be applied to interpret a phase diagram, the starting point would be a very simple system like a one component system in which we have only one solid, one liquid and a gas phase. That means such a system will have C is equal to 1, it is a one component system, and the maximum number of phases is 3. To this system, if we apply the phase rule equation, we can find out the number of degrees of freedom for this system. First of all, we have to find out what is the maximum value of F. We can get it by keeping P minimum, that is P is equal to 1. This is the phase rule equation. F is equal to C minus P plus 2, and when C is equal to 1 and P is equal to 1, we get maximum value for F, and in this particular case it will be 2 degrees of freedom, the maximum value, and therefore we are at liberty to choose what will be our variables. And generally we use pressure and temperature as the variables, and the phase diagram is constructed by studying the equilibria between the phases present in the system under different combinations of temperature and pressure. If we consider water as our system, we have to have a container in which the water is taken, fitted with the piston, by means of which we can vary the pressure, and there can be a device to increase or decrease the temperature. And by studying the behavior of water under various combinations of temperature and pressure, we will be able to get the various equilibria that are present in the system. In one component system, therefore, if we look at one phase equilibrium can be there. We have one solid, one liquid and one gas. The system will be a bivariant system for which F is equal to 2, which in the phase diagram is represented by an area, because we need to specify pressure and temperature in order to define the system completely. And if there is a two phase equilibrium, the system becomes a univariant system. That means F is equal to 1, and it is represented by a line, one line, and there is a second line and there is a third line, indicating that there are 3 two phase equilibria in this system, for which if we fix pressure, the temperature becomes automatically fixed, that means it is univariant. Alternatively, if we fix temperature, the pressure becomes automatically fixed, and if there is a 3 phase equilibrium, the system becomes invariant, for which F is equal to 0. It is represented in the diagram by a point. In this particular case, it is the intersection of the 3 lines for which the temperature and pressure both are fixed by the system. That is why it is called the invariant system or the invariant point. You can also call it a triple point. Hence, in the diagram for a one component system that has one solid phase, one liquid phase and a gas phase, there will be 3 areas, there will be 3 lines and a point. So, one area each for solid, liquid and gas. And in this diagram, you will see 3 areas 1, 2, 3. Now, how will you identify where the solid or the liquid or the gas phase exist in this? We know the favorable conditions for stability. If you take a gas and you compress it, it becomes a liquid. You may have to decrease the temperature as well. Therefore, the condition for a gas to remain in stable condition, the temperature is high and the pressure is low. If you increase the pressure and decrease the temperature, it is likely to become a liquid, and further compression may lead to solidification. Therefore, high pressure and low temperature favors the solid phase. So, you have the region identified as solid, which is at high pressure and low temperature, and the liquid comes in between. So, it is possible for us to identify the three areas: solid, liquid and gas, and the boundaries that separate them give us the two-phase equilibria. We have solid liquid, liquid gas and solid gas equilibria in this. So, any one component system that exists in one solid, one liquid and a gas phase will show a phase diagram of this type. The best known examples: water system and carbon dioxide system. What is the difference between the two? They will differ only in the position of the lines, otherwise the overall nature is the same. But as we shall see later, carbon dioxide system gives us a phase diagram which is representative of a one component system. Water phase diagram is an exception. We know that water always shows anomalous properties. Have a look at this diagram. We have the line that separates liquid and gas, where this line will lead us to. Similarly, where the line that separates solid and gas leads to, and the line that separates solid and liquid. We can answer this. The line that is the boundary between solid gas, that means where solid and gas remain at equilibrium, theoretically will lead us to 0 degree absolute. The line that separates solid and liquid will take us to a region. In many of the cases, you will find that different solids of the material come into existence at very high pressures, including that of water. But the line that separates liquid and gas, which gives us the liquid gas equilibrium conditions, terminates abruptly at this point, and this point is called the critical point, which is characterized by critical temperature. It is the temperature above which a gas cannot be liquefied no matter how great the pressure is. Similarly, we can define the critical pressure. It is the pressure beyond which a liquid cannot be vaporized no matter how the temperature is. How to look at this? We can say that a gas at the critical point is at such a high pressure and its molecules are so close together that it becomes indistinguishable from a liquid. Similarly, a liquid at the critical point is at such a high temperature that its molecules are relatively so far apart that it becomes indistinguishable from a gas. That is what we want to say. Gas and liquid become indistinguishable. The two phases simply become one and form a supercritical fluid that is neither true liquid nor true gas. At Tc, a whitish pearly sheen momentarily appears and the visible boundary, that is the meniscus between the liquid and the gas, suddenly vanishes. This is the region in which the supercritical fluid exists. You are familiar with the experiments which are known as Andrews experiments on carbon dioxide, which define the critical temperature and the critical point. That means once the phase diagram is ready with us, it is possible to extract a lot of useful information from the diagram, as we shall see later. But for the moment, let us look at another problem. This is the problem that you face in the lab. We always check the melting point or boiling point of the substances in order to identify them. That means boiling points and melting points are taken as characteristics of these substances. Let us try to find an answer to it and find out where phase rule can help us. A pure compound, which means the number of components is 1, C is equal to 1. We are heating it, we take it in a capillary and melt it. As we heat it, a stage comes where melting begins. That means there will be an equilibrium established between solid and liquid. The number of phases therefore will be 2 in equilibrium. To this, let us apply phase rule. F is equal to C minus P plus 2. In this case, C is 1, P is 2, so that 1 minus 2 plus 2, we are left with 1. The number of degrees of freedom available to us is 1. What we do? We take the melting point and boiling points at 1 atmosphere. That means the 1 degree of freedom that we had, we have utilized in fixing the pressure at 1 atmosphere. We are left with no degree of freedom. Therefore, the temperature cannot vary as long as the 2 phases coexist in equilibrium. Therefore, whenever we take the melting points, we must remember that if the compound shows a sharp melting point, it is pure. Let us verify this. Take an impure substance containing another impurity in it. When an impurity is present, it becomes a 2-component system, for which C is equal to 2 and P is equal to 2. And we can apply phase rule and try to find out the number of degrees of freedom when the equilibrium between solid and liquid is established. F is equal to 2 minus 2 plus 2, which means the number of degrees of freedom now available to us is 2, one of which we are using to fix the pressure at 1 atmosphere, but we are still left with 1 degree of freedom, and hence T can also vary. That is why impure compounds melt over a range of temperature. In our day-to-day life, as I told you, how a pressure cooker works, why the food gets cooked faster, how the skaters are able to glide fast on a skating rink where there are no wheels in the skates. It's an ice rink. And similarly, especially when you have a snow covered road, in order to clear the snow, sometimes a white powder is sprinkled, the road gets cleared. Such diverse questions can be answered by the application of phase rule. Now, let me summarize what we discussed today. We started with the derivation of phase rule equation by considering the total number of intensive variables for a system consisting of large number of phases and large number of components in it, and then subtracting the number of variables that are automatically fixed because of the equilibrium conditions to give us the answer, that is the phase rule, F, the number of degrees of freedom. And also we looked at how to use the phase rule equation, some diverse problems I mentioned, and as we move forward we will get more such problems and try to answer them.